Hey, it's 11:45. We're running a few minutes behind, but I'm really excited to introduce our final presenter, Catherine Crouch. Catherine and I have known each other for a very long time, since the moment that Catherine actually came as a as a graduate student to Harvard, a PhD student in my department. And I remember meeting her. I said, "God, I'd love to work with Catherine." She chose one of my colleagues as PhD advisor, but I had the good fortune of having Catherine in my group for 5 years after she obtained a PhD, where she pulled a pretty incredible feat. She worked on both physics education research as a PhD student and on materials physics. She's now a professor at Swarthmore and has devoted quite a bit of her effort at putting physics in the context of the life sciences. So Catherine, welcome here. Thank you for joining us. I think you'll find a very eager audience. So I turn it over to you.
Great, thanks, Eric. Can you facilitate my screen sharing? I just tried to do it.
Yes,
Um,
yes,
so it's
yes.
really great to see all of you on my screen. I wish I could actually be with you in person. That would be much more enjoyable. But what I want to tell you about today, I did change my title a little bit. You're always thinking it over and like, what is the message I want to get across? And what I realized for all of you as high school teachers is that I want to emphasize the ways in which our course seeks to support both interdisciplinary learning and enduring learning, learning that goes beyond the confines of just our course, but lasts. And I'm excited that at the end of the talk, I'll be able to share some results very recently obtained about that. But what I wanted to take a minute and reflect on for a little bit is that for you as high school teachers, you may not be in the position to teach a group of students who are all united in a common purpose, that they want to become life scientists or physicians eventually. But I wanted to start out by sharing two principles of educational psychology that have been essential in how I've designed this course. And I think that these principles will connect to you regardless of how much commonality there is among the motivations and interests of the students who you teach. And in the discussion period at the end, I'm hoping you can take some time to reflect on these principles. And as you listen to my talk, I hope you will think about how those principles pop up. So the first is what is called expansive framing. And it's the idea that when you teach a class, you tell the students that this is not just about doing well in the class, but this is actually meaningful for the long term. And an educational psychology experiment was done by the late Randy Engel from Berkeley and her colleagues, in which high school students were tutored about the circulatory system. And in one case, they were tutored about this in a way that basically said, this is for you to learn for this class some important principles. And in the other framing, it was talked about as this is broadly relevant understanding of science. This is applicable outside of what you're learning in school. And it turned out that then when those same students were then asked to learn about the respiratory system, the students who were tutored with that broadly relevant framing, where they were repeatedly emphasized that they weren't just learning this to take a test, that they were learning this for broad purposes, that they were more successful in applying what they had learned about the circulatory system to understand the respiratory system. This concept of expansive framing, thus, of really explicitly as a teacher emphasizing to the students that what they're learning has lasting value, And of course, all of us intend that, right? But sometimes we have to actually say it to our students to communicate it. This has been very important to me as I've built this class. The other thing that I've been impressed by is how much communicating the relevance of what we're teaching can be meaningful, especially to those students who need our support the most. Another intervention done by Hellman and Harakovich did a randomized, blinded, and controlled trial. So gold standard in ed psych, nothing I will show you has quite this much control of it. A bunch of 9th grade students were assigned to reflect on the utility and the relevance of material they studied in science to them personally. And then the control condition, they reflected on something unrelated. What they found was that for any students who had low initial expectations of succeeding in the class, both their course grades and their reported interest in the material increased. And so to me, again, as I think about teaching physics to life science students, but for you all, as you think about teaching physics to your students, whoever they are, this giving students opportunities to make connections to why this is relevant for them, why they might care about it, I think is a tool of incredible power. Okay, so now on to my course and what we've studied. So you might ask the question, if you're teaching a college physics course for life science and pre-med students, what are the most important goals for that course? And I believe that the most important goals for that are to both prepare and also motivate life science students to use physics tools in their future work. It's not to help them get a good score on the MCAT. It's not to help them boost their GPA. It's a long-term investment, because I am convinced that the life sciences and medicine increasingly rely on their practitioners being capable with the content and methods of physics. So this is the goal that I'm trying to achieve with this course. And so what I'm going to do for the rest of this talk is talk about how we've designed this course to try to accomplish these goals. Share with you just a few highlights of what our assessment has shown that our students get out of it. And then give you the chance in your discussion to take these principles and think about how you might leverage them in your own teaching. Okay, so first the design of the course. Because of this issue of the expansive framing that I laid out before, I'm convinced that it is important not just to demonstrate, but to actually explicitly tell students in so many words, this course material will be valuable in achieving your long-term goals. And also that as you go through this course, it's your job to be trying to connect the physics that you're learning to the other science you know, because the setting in which you're going to eventually use it is not a physics classroom, but it is the life science research or the medicine practice that you want to engage in. So this is the message that we seek to get across to our students. To accomplish that, in the design of the curriculum, we've sought to combine the wealth of knowledge that people have already developed about how to teach physics well. So I got to work with Eric, my goodness, 25 years ago by now, on developing effective ways of teaching physics. It takes work to figure out how to teach physics well. You don't want to throw all that out and start over. You want to leverage that. But to combine that knowledge with understanding how life scientists and medical professionals encounter and use physics. And so one of the critical elements of this course is what another one of Eric's and my colleagues, Jessica Watkins, described as authentic connections to biology. Basically, what's a problem or what's a situation in which a biologist or a physician would agree that physics gives you meaningful insight into the problem? Not sort of superficial, you know, you're throwing a pumpkin instead of throwing a baseball or whatever, or you have a problem where you have a cheetah running, but the cheetah running could equally well be a car driving, and it doesn't take into account any of the real complexity of how actual big cats run, or why they run, or under what circumstances they run. Instead, we try to make it possible to always have the appearance of biology in our course be actually ways in which a biologist or a physician, if they were sitting in the classroom, would be like, yeah, that's how I would think about physics coming up in my field. And so we've developed a structure for each unit where we begin with the biology motivation for a topic. Why are we teaching this topic? How does it fit in to a long-term understanding of biology? But biology is pretty complicated. It's messy. It's a very complex system. And so then we tell students, in order to help you understand this topic, we're now going to move to what you might call a physics context, the kind of situations that physicists and teachers of physics have developed over decades as ways to helpfully understand these principles, so that you can get on top of the principle and feel comfortable with it and understand it. But then, don't worry, after we finish grasping this topic in the context of physics, we will move back to biology to apply it to a biological problem. So you'll learn it in the physics context for the sake of developing your skills so that you can then apply it to biology. And then sometimes we cycle around this numerous times for a given topic, because sometimes there's more than one useful and meaningful, interesting example. So we have really tried to restructure our course around topics for which we can give an authentic biological motivation. So for the first semester, you see some familiar looking stuff, kinematics, forces, energy. But notice this insertion of random walks and collisions early in the syllabus of the course. That's because diffusion, osmotic pressure, other phenomena that rely on statistical physics are of critical importance in biology. When we were designing our course, we discovered both that these were topics that biologists and physicians agreed were really, really important and that weren't taught anywhere in the curriculum in chemistry or biology until physical chemistry. That's a junior level course for chemistry majors that many of these students never even take. So we decided we've got to get some statistical mechanics into our intro physics for life sciences class. So we inserted it right after kinematics. So we've organized each of these units around the connections that they make to biology, where they give meaningful insight, biology or medicine. And so, for example, you'll see in fluid statics and dynamics, our big connections are to the circulatory system. So I've got a list here of the topics we cover and the connections that we make to biology. I don't expect you to grasp them all. We've selected the physics content that's the most important while still keeping the storyline. So what you might have noticed is we left out nearly all of rotational dynamics. So going back to that slide for a second, we do forces in equilibrium. So we do torque balance in equilibrium problems, but we do an absolute minimum of angular dynamics because it's just not that important for very many situations. There are a few exceptions, but we mostly leave it out because there's just too much else that's really important. Kinematics, though, arguably kinematics is not that important for biology, but it's so foundational for understanding so much of physics. It builds a vocabulary that's required that we felt that we couldn't leave it out entirely. And in particular, it does help in understanding diffusion and random walks and so on. So we have really minimized the discussion of kinematics and streamlined it in order to make more space for other things. So that is how the first semester is designed. The second semester, similarly, optics is centered around animal vision and microscopy, waves around echolocation, and then diagnostic ultrasound is an application of echolocation, electricity and circuits, magnetism, and induction. Now you might say, does induction have any biological relevance? Very, very little. I have actually developed a problem about pacemaker safety, which students actually find incredibly boring. But students love the fascinating counterintuitive nature of the kinds of demonstrations you can do with magnetic induction that connect to magnetic braking in hybrid cars and so on and so forth. And so what I've found is that induction provides some of that sort of joy and excitement and wow, this is really cool and fascinating element that is really wonderful and important to include in a physics course. And so even though there's very, very minimal connection to the life sciences, I've left it in because I think it plays a really important role for the students in the course. Many of my colleagues who teach these courses have found ways to fit in nuclear physics and others and spectroscopy. I think those are really important topics. I haven't personally found a way to fit them in to the second semester, but those are also topics with many wonderful connections. And some people do less than I do with the connection with electricity and circuits to neural circuits. And so there are definitely adjustments one might make. So I've outlined for you what the content is that we cover. It's also really important that physics is an opportunity to develop a whole suite of scientific skills. The idea of building a simple model, the idea of sort of rigorous qualitative and quantitative reasoning, like proportional reasoning around things, dealing with multiple representations, going back and forth between a graph of data, an equation, and a verbal description of something, working with quantitative data. These are all skills that when we've surveyed life scientists and physicians, they say these are really, really critical skills for our profession. And physics is a really great place to develop those skills. And so I'm also convinced that our course is intended to help cultivate these kinds of skills in students. It's not just about teaching them physics content and teaching them how to apply that content to a biological situation. It's also about teaching them what you might call the way that physicists think. So these are the three elements of our course design that are central to how we decided what to include and how we developed that sort of instructional cycle. The last thing I will say is it was central to our course that we use research validated pedagogy. And so our courses are taught with concept tests, with context-rich problems, with students being engaged actively. And that has involved as much as possible leveraging materials that were already developed by the physics education community for how to teach material effectively, and then adapting them for these particular areas. Okay, so that was all very abstract. Let me give you just one example of how this works in terms of curriculum. And there are many, many more examples that I could either describe or that you can look up later on the course, on the portal website that is being developed to share these materials. So this particular example is from optics, which is one of my favorite topics to teach in this because students get really excited about it. And I think it illustrates nicely that physicists and biologists may use the same ideas, but they may apply them in very different circumstances. And so in our course, we try to give the students the flexibility to apply them in both situations. What do I mean? Let's do the example. Let's think about forming images with thin lenses. The usual physics problem, if you've got a thin lens problem, the lens has a fixed shape, and so it's got a fixed focal length. And so the problem is about you're moving your object around, or you're moving your lens around, and where does the image go, and what kind of image is it? So that's a useful kind of problem to learn to solve, and we do that with our students in that physics stage. But human vision doesn't work that way. Our eyes have a fixed retina and an adjustable focal length lens, as is illustrated here. So if you're going to see clearly, the image distance has to stay the same. The image distance has got, sorry, not the image distance, meaning the distance from the lens to the retina. You've got to form a focused image on the retina. You're looking at something that's out there, so often you don't have control over where it is. So the object distance has to stay the same. What can you change? You can change the focal length of the lens. So after doing some standard concept tests that one would do about helping students understand physics-y type lenses, we switch to this sequence of concept tests. Suppose you're in a garden and you're looking at a flower. Then you turn your gaze to a tree that's farther away. How does the focal length of your eye's lens change, if at all? If this was a physics meeting rather than a meeting about teaching, I would probably, and if we were in person and I could actually like hear you all talk to each other, I would let you think about this and talk to your neighbor to answer it. But I will just say, you know, your focal length increases to look at a more distant object. So now the students are then asked to think about the same situation and say, how does the shape of your eye's lens change to accomplish this? Does the lens become rounder, more curved, flatter, remain the same, need more information? And so again, they would talk with one another, reflect, and arrive at the conclusion that the lens flattens out to give you the longer focal length. So this is just one illustration. And as I said, I'm part of a consortium of about a dozen institutions around the country that have started building this thing called the Living Physics Portal, which is an open source and free set of resources for teaching physics this way. And I've just noticed that the slide that I grabbed out of an earlier talk is old, is a year out of date. It's not even in beta anymore. You can get this for real. You can sign up. And so if you're interested in seeing more of the materials that we've developed for this class and that other institutions around the country have developed, it's available at this URL. And you can sign in as an instructor. You get validated as an instructor. If you're a member of the American Association of Physics Teachers, it's very seamless. If you're not, they have other ways to validate that you're an instructor. And then you get access to solutions and things like that, where students have very, very limited access so that the integrity of these instructional materials is protected. So this is a great way to share ideas. And one of the key lessons that has come out of this collaboration of a dozen institutions teaching these courses is that people are teaching different populations of students at their home institutions. And so every course like this is a little bit different and leverages ways that their students connect to the material particularly. leverages particular kinds of courses at their institution or particular emphases. Some places have physical therapy students and have developed lots of materials related to physical therapy. Swarthmore doesn't have any future physical therapists, at least that I know of. We don't have a pre-physical therapy program. So my set of materials are for pre-med students and students who want to go on and become research biologists. So this portal is a great place to find a really wide variety of materials. Okay, so that was the 20-minute introduction to this curriculum. And from what I understand from Eric, the way you all have been working is you've been doing questions at the end. So what I now want to do is go on and tell you a little bit of what we've learned that students have gained from this course, from our assessment. And then at the end, I'll be glad to answer questions about either the curriculum or the assessment. So what do students get out of this? First, I want to just thank my research collaborators. This is the first round of research collaborators from the first stage of assessment of this course, involving several students and also several colleagues. And in the interest of time, I'm just going to highlight the key findings, some of the key findings we've had, and not delve so much into the methods, but I'll be glad to share about those. So one is that our students report that indeed they do leave our courses feeling that physics is useful and relevant for the life sciences. And one of the very first things we did to assess this was a question on the course evaluation that I think helps capture this, although we've subsequently followed up with much more rigorous evaluation of this. So in the 2012 course evaluation, we put a pair of two statements that we asked students to select choices to complete. The first statement was, at the beginning of this course, I considered physics to be, and they had to choose one of four answers: very useful, somewhat useful, of little use, of no use in understanding the life sciences. So you can see that at the end of the semester, as students are reflecting back on what they remember thinking at the start of the course, they thought at the start of the course that physics was somewhat useful. Then we asked them to say, now at the end of this course, many more of them say very useful, almost all the rest say somewhat useful. You can't win them all. There's one of little use, and there's one disgruntled curmudgeon who now says that physics is of no use. Well, oh well, can't win them all. And then we repeated that in 2013 and 14, and I'm happy to say that in those years there were 0 of no use responses. So this is just asking students to say, how has the course changed their own understanding of how useful physics is? And from before the course to after the course, they perceive that this course has helped them see it as of more use in understanding the life sciences. We did an extensive study using the CLAS, the Colorado Learning Attitudes About Science Survey, the punchline of which is that our students develop greater interest in physics, not just in biology, but actually in physics in the course of our curriculum. And in the interest of time, I'm just gonna click through this and go on to the next item just because it's kind of technical and detailed to go through how all it works. But then the thing that we've recently found that I'm really proud to say is that we've found that these attitudes last for a year or more. We've recently been able to do follow-up surveys on students a year afterward. A student of mine, Gwendolyn Rack, who's a rising junior, just finished analyzing these data this summer, so I apologize for the slightly scattershot nature of the slide. If we look at students who were only able to take the second semester course, we asked them to respond on a set of items that were developed by Christy Hall at the University of Maryland as part of her PhD student, rating the relevance, usefulness, and utility of physics to their interest in biology. And we scaled those so that 0 is basically neutral, positive numbers are positive, negative numbers are negative. And what we see is that students coming into the second semester of our curriculum, having not taken the first semester for reasons related basically to scheduling, those students come in mildly positive. But then after taking the second semester, they become significantly more positive. So they go from, they go up about half an increment. And so the conclusion for this is that they view physics as much more connected to biology after they've taken this one semester. And what Gwen has found, that I'm going to show you on the next slide, is that following up a year later, they're basically staying in the same place. So this blue histogram corresponds to the same population as I showed you before. It turns out that if students have had 2 semesters of IPLS, they go even a little bit higher. But basically, this statistical test is testing, is there any difference between what they answer on the follow-up versus what they did at the end of the second semester? And the conclusion is there's no difference. This p-value means no difference. So we're excited to see that even a year later, after students haven't had any more physics, but they've taken more biology classes, they've done research, they've volunteered in hospitals, they've done EMT training, these positive attitudes last. Another thing that we've delved into, and this has mostly been the work of my colleague Ben Geller, is to try to understand what it is about the course that students say leads to these positive attitudes. So he and my colleague Chandra Turpin from the University of Maryland have done a huge amount of work interviewing students and analyzing qualitative responses, open-ended writing on surveys. And the thing they conclude is students are not all the same, which at first, it's like, duh, students are not all the same. But what's actually really encouraging about this is what they found is that there are many different ways that students report nonetheless feeling that the course helps them succeed in making the material meaningful and relevant and exciting. What this diagram is showing is that they've basically identified 4 different pathways represented by these, by these black arrows, by which students report feeling like the course engages them in a meaningful way. 2 of them relate to kind of the coherence of all the different sciences, whether it's by making connections between different sciences or by this sort of feeling of like, oh, it's all one thing, it's all connected together. So those are similar. Other much more practical students say, well, this seems relevant, it seems useful. Or they even say, because I feel comfortable with biology and I understand biology, this made physics feel more comfortable. It made it feel more accessible than it did before. What I love about these findings is that it says that this course connects to students in a variety of different ways. They don't all have to find the same way to connect to that. And I think that's really helpful for us as teachers, because we all know that our students are not all the same. And so it's encouraging when you can see that a course can be built in a way that different students can connect to it. So the last highlight I wanted to share with you, I said at the beginning that our goal was to help students become not just motivated to apply physics in their future work, but also to be prepared. So I've hinted that it makes them motivated, but I haven't said anything yet about are they prepared. Well, did we succeed? Well, this is hard because you have to test students later. You have to test them in what's called in the field a longitudinal study. You got to track students down when they're not in your class anymore and test them and do things. So for this, we were fortunate to have an NSF grant. And so you can see we have a small army of undergraduate students who've been part of it, as well as 3 colleagues. I already showed you Gwen's work on the attitudes. So I want to just end with sharing with you the key finding that Jack, I forgot to put his picture on his slide, has found. We were able to work, thanks to my colleague in biology, who is our co-PI, with the senior biology capstone course. And we were able to get one of their class periods to assign them to do a task related to diffusion, where we asked them to do some quantitative analysis of how diffusion plays out in animal digestion. And the details of this aren't that important, but essentially in the gut, you've got high concentration, in the blood, you have low concentration, and we asked the students to think about how diffusion happens from this region where there's high concentration to low. And the task required that they do some graphing of concentration versus position, describing the mechanism that was involved in the diffusion happening, do comparative work comparing graphs that we provided to them, and to apply Fick's law, which is actually introduced in one of the biology classes, but in a very kind of minimal way. And so the task introduced Fick's law to them, explained what it was, and asked them to use it. So Jack learned a lot. I'm going to just take a minute to share one of the key findings he had, which is that the students who took the life science physics are able to flexibly apply physics to this biology problem. So what's shown here is 4 sets of students, those who had had no college physics. They had all had high school physics, but they had not taken any physics at Swarthmore. Those who'd taken physics but not our curriculum, those who'd taken our curriculum concurrently with their senior biology capstone, and those who'd taken it 2 years earlier. These box and whisker plots, the lines in the middle of the boxes are the medians, the individual dots are the individual student responses, and then these whiskers out here show the maximum, and then the lower extending one over here show the minimum. So this is a kind of a souped up bar graph that is actually used a lot in biology to let you see the distribution on a bar graph. And so like what you can see here for the no physics students, 4 of them were not able to do anything on this task in the parts that required them to use physics, as opposed to in the parts that just required them to do reasoning with graphs that we gave to them. One of them earned this score, one of them earned this score, one of them earned this score. Whereas over here, you see there were a couple of the students who were concurrently enrolled in the life science physics course who also couldn't do any of the physics parts of the task. But you see these scores corresponding to much greater achievement on the task. And then what we were so happy to see is that even 2 years later, these students were able to apply the physics that they had learned 2 years ago to analyze this situation. I want to emphasize how happy we were and how meaningful it is that they were able to do this, because students talk about diffusion in biology all the time. It does not necessarily prompt them to think, oh, I need to use physics. The way the task was presented, the students were encouraged to draw on anything they had learned anywhere, but they were not specifically told to use physics because not all of them had even taken physics at Swarthmore. So the students who came up with this did it on their own. It's also documented that students find it hard to take something they've learned in one setting and move it to a very different setting. So what we were really pleased is that our students were able to flexibly use this physics in a biology, sitting in a biology classroom in the context of a biology task. And they were able to do it 2 years after they took our class. So we were happy about that. Okay, so that's the end of what I want to share with you. I've described the design of our curriculum. I've highlighted our successful outcomes, and I want to really thank both our sources of funding and the many faculty colleagues who shared their expertise and their discipline with me to help me figure out what to include in this curriculum. And I left it mostly off of this slide, but I also want to thank all the many colleagues who are part of this Living Physics portal, who have also developed other courses like this and who sharing ideas with over the last however many years I've been working on this has been also critical to my development. So thank you, and I'd be glad to take questions now before we do the discussion.
Thank you so much, Catherine. This was great, and it sort of matches so well with the previous talk in a different dimension, and might also help frame our discussion this afternoon. I see 3 hands up. John Machuk, you are the first one. Please unmute yourself.
All right. Thank you very much. That was really interesting material. We're having a very active conversation in the chat area about different things to do. But I did go to the Living Physics portal already, livingphysicsportal.org, and it does still say that it's in beta. I think you said that it's no longer beta. Is there a new website, or do we just need to update our links, or what?
It may be that so I'm on the content side, not the web developer side. It is possible that once you get instructor access, it is, but if you run into any problems, actually accessing content, like if you go into that and you can't register or you can't use content, I guess probably shoot me an email. Eric will know, Eric or Sarah can point you towards how to reach me. And then I will find out like what I overlooked from the web developers.
Okay.
So and while you all are doing the discussion, I'll check on that also. So
I have registered and gone in through my compadre account. I am now listed as pending. So
okay.
I'm awaiting with bated breath.
Well, it may be that the beta designation is still on the public facing stuff.
Okay, well, I'll cross my fingers and hope I get in there.
Great.
Andre, you have your hand up. You're next.
Okay, Catherine, hello. Nice to see you after about 25 years. I saw
Great
you
to
at
see you. Yes,
yeah.
My dad still talks about the rectangle. You're calling it the rectangle of life.
Yeah, very nice to see you. Hope your dad is doing well. Very impressive work in many respects. But since I'm an old curmudgeon, I want to quibble with just one thing. I would suggest that you really need to include rotations, at least rotational kinematics. It is a physics course. It's very hard to make sense of the world if it is happening along a straight line. And there are many, many biological situations which require rotation. And I'll just add just one thing. You had as one of your topics, NMR. Well, how do you understand NMR without rotation? And I don't want to detract from your very nice work. I just want to make a plug for rotational stuff, which is also very good.
No, and Andre, I really appreciate your asking that question. And as all of the rest of you can tell, I've also known Andre for like 25 years, so he feels comfortable doing this kind of thing. So first of all, we do take one class period to discuss the idea of angular momentum as the rotational analog of linear momentum, for exactly the reason you described, that understanding the concept of angular momentum is important in understanding chemistry because it gets talked about a lot. We focus purely on understanding it conceptually rather than doing calculations of angular momentum. So we don't get into, L equals R cross P, all the different kind of crazy cases that you have to be able to evaluate, but just the sort of simplest examples of how to do that. So you're exactly right that in order to understand NMR, you need at least a rudimentary understanding of angular momentum. As for what to include and what to leave out, I will just say that this is the subject of a constant lively discussion on the Living Physics Portal team, as well as everybody else. And that if we could make all the life science students take 3 semesters worth of physics, we would have no hard choices to make. But I completely agree with you that there are cases of relevance.
Thank you. Next in line is Grastan, and then we'll have Kelly, and then we'll transition to breakout rooms. Yes, go ahead.
Eric, let me just clarify, because I saw the question in the chat. Yes, absolutely, we delve into torque, but we focus on torque in equilibrium situations. So we do a number of quite complex biomechanics problems where where situations are balanced, and you can actually demonstrate with those why it causes so much strain on your back, for example, to try to lift improperly, to sort of lift from your back rather than with your knees, entirely with an equilibrium analysis. And we just, again, it's just for lack of time. I mean, Andre is exactly right that if we had more time, there would be interesting biomechanics dynamics to do as well.
Yeah, very interesting talk. Okay, since Andre talked about rotation, actually, rotation is very, very relevant in flagellar motion.
Yes.
And so I actually taught a graduate course, physics for biologists, and this is one of the things that we discussed. Maybe some of you know that 13 years ago, I developed this program called Physics of Living Systems. So since then, I have funded hundreds of people working on physical principles in biological systems. And there is virtually no, including Eric, virtually there is no area of physics, maybe quantum gravity, but we don't know that anyway, that cannot be taught through biology. But I had, and I'll talk a little bit more in the afternoon about the effort that we have undertaken with Eric and other people that are funded by me. My question actually is quite concrete. First, what was your enrollment compared to, let's say, physics for poets? And second question is also concrete. Which course does that substitute? Does it substitute physics 1, physics 2, physics with calculus, physics for poets? Or so in the curriculum of a student who is going to a medical school, they have requirements. So where does this stand?
Yes, great, thanks. So Swarthmore is a little unusual in that before I created this course, we only had a single introductory calculus-based physics course. So the engineers and the life science students were all in the same thing. We have separate courses that are, like you say, the sort of physics for poets, the courses that are designed for students who are just interested in learning something. Those are not year-long survey courses. So this this added a second year-long introductory 2-semester sequence of physics. And so it split apart the enrollment that we had in the original single course from roughly 100 each semester to now the engineers course is roughly 40 each semester and the life science course is roughly 60 each semester. Swarthmore is a small school. Our total student body is 1,600 students. So those are actually pretty large numbers proportionally to our student body. Now, at Swarthmore, it is still a calculus-based course. It's what we call calculus light. We focus on using differential calculus extensively, so students take lots of derivatives, but primarily using integral calculus in the form of interpreting functions graphically, so interpreting the area under the graph as the integral, and only doing integrals that are very simple, you know, like integrating a polynomial or something like that, so that the techniques of integration are not something that students are expected to really have at their fingertips. And the reason for that is that Swarthmore, as a student population, pretty much all students have taken some calculus when they get to our school, and they're all required to take 1 semester of calculus for the different majors that they would be in this curriculum for. However, they almost all take that calculus the first semester of their freshman year or place out of it based on high school. They get to our curriculum, their sophomore or junior, or sometimes even their senior year, and it's very rusty. We can call back the derivative taking and the conceptual interpretation of the integration very quickly. We would have to spend a lot of time reminding them how to do integrals, and we just don't think it's worth it, because the reality is these students, if they go on in their other fields, they're going to be doing numerical integration, right? They're going to be programming computers to, or using computer code to do any integration they need. That said, something that would be high on my wish list would be to actually do some computation in this course to give them computational skills. It's something I have also not figured out how to fit in. Some of my colleagues have. So on the Living Physics portal, in places you'll find computational activities, either just using spreadsheets or using like simple user-friendly Python notebooks. So people have kind of very different attitudes to how much they use computation, how much they use calculus. The Living Physics portal includes a number of courses that are truly algebra-based courses where they don't use any calculus. So if that's the angle that your institution takes, that's feasible.
Thank you.
Okay, one more question, Kelly Miller, and then I'll let Catherine handle how we're, or say how we're going to handle the remainder of the time. Kelly, go ahead.
Okay, thanks. Hi, Catherine. Thanks a lot for your talk. I just have a really quick question about the methodology. And you mentioned that when you're trying to measure how like students' ability to see the relevance of the physics in the biology classes, you ask them at the end of the semester to reflect back on how important they thought the physics was at the beginning of the semester. I was just wondering about that choice of like, why not ask them at the beginning of the semester and then at the end of the semester? Why ask them to reflect back? The reason I ask is because it's like I'm doing something similar, and I sometimes question whether like the experience itself affects their ability to like reflect back, if that makes sense.
So the short answer is that most of our attitudes data are pre-post, and everything that I showed that was with the follow-up, that was done with pre-post and then 1 year later follow-up. I started with that one course evaluation question just because I think it's kind of quick and easy to see what the bottom line result is there, and also because I do think it is meaningful to ask students, you know, how do you perceive that your attitudes have changed? But you're exactly right that raises a different set of methodological questions than pre-post. And so we've done both pre-post CLAS using items in the CLAS, and we've done pre-post and follow-up with this inventory developed by Christy Hall at University of Maryland. And so that's all multi-time point data.
Okay. Okay.